Okay, so for this next chapter, we're going to start taking a look at curve sketching. So to find the x-intercepts of y is equal to f of x, we already know from previous courses that we have to set y is equal to 0, and then we're just going to solve for the x values. On the other side of things, if we need to find the y-intercepts, we're going to set x to 0 and then solve for y. An even function satisfies the requirements that for all x in its domain, if I took f of negative x or I took f of positive x, then they would be equivalent. The graph of an even function is always going to be symmetrical about the y-axis. So let's take an example. Let's take y is equal to x squared. Now this is an even function that I already know is going to be even or symmetrical about the y-axis. Where I'm going to have any point that's given, if I had negative x and it gives me a y, I could have a positive x and it would give me a y. And these ones, we already know from grade 11, are always going to be symmetrical like that. Now, why does this work? Well, if I took y is equal to x squared, and I take f of x for this, f of x we already know is just going to be x squared. If I take f of negative x, then that's going to give me negative x squared. And in this case, I have to square the negative and square the x, which is going to give me positive x squared. Because from what I've seen here, my f of negative x and my f of positive x are the same value, I know that f is even and as such should be symmetrical about the y-axis. If I try and apply the same logic to an odd function, well, let's take a basic odd function. In this case, I'm going to choose the odd function y is equal to x cubed. If I have y is equal to x cubed, it runs through the origin, and it looks something like this. If y is equal to x cubed, then f of x is x cubed, and f of negative x is equal to negative x cubed, which is still just the negative of x cubed. We can see that my f of x and my f of negative x have the same value, except for in one case it's positive and in one case it's negative. So we could write, like it says up here, that f of negative x would be the same as the negative version of f of x, meaning that f is odd, and as it states right up here, it has rotational symmetry, about the origin. So I have an x and a y here. I have the negative x and negative y here. And it's rotated for that point about the origin. For example 1, it wants us to determine the intercepts of the curve y is equal to 3x cubed plus 8x squared minus 5x and minus 6. We know that the y-intercept when x is equal to 0 should just be the constant term. Of any polynomial function. Therefore, if I cancel all of these out, then I'm just looking at the end here, and I'm going to state that it's going to be when y is equal to -6, or it occurs at the point of 0 and -6. For the x-intercept, we're going to solve for when y is equal to 0. So if 3x cubed plus 8x squared minus 5x minus 6 is equal to 0, then we're probably going to factor using synthetic division, and we're going to find when our f of x which we're going to say is 3x cubed plus 8x squared minus 5x minus 6 is equal to 0. Remembering that to do this, we would take a look at the possible factors of our constant here. So positive or -1, positive or -2, positive or -3, or positive or -6. Conveniently enough, when we try +1, then I get 3 times 1 cubed is just 3 times 1, which is 3. 8 times 1 squared is just going to give me 8. -5 times 1 is -5, and minus 6. And that does wind up equaling 0. So from that, we know that x minus 1 is a factor of that f of x, or is a factor of 3x cubed plus 8x squared minus 5x minus 6. We're going to use our synthetic division to factor this down. Remembering that if we do it right, we should have a remainder of 0. We're going to carry the first term down. 3 times 1 is going to give me 3. Add them together and I get 11. Times 1 is going to give me 11. Minus 5 and positive 11 give me positive 6. 6 times 1 is going to give me 6. And positive and -6 give me that magic number I was looking for, 0. Which means that we can state that f of x could be rewritten as x minus 1 and 3x squared plus 11x plus 6 from here. Remember, we are using 0 for f of x. And we can factor this trinomial down using decomposition or whichever method you prefer into 3x plus 2 and x plus 3. Meaning I have x-intercepts at positive 1, at negative 2 over 3, and at negative 3. For example 2, we're going to determine whether each function is even, odd, or none of the above. So remember, when we're trying to determine even versus odd, we're trying to solve for what the f of x is. Well, it already told us this. And we need to solve for what the f of negative x is. Now, anytime we have it where our f of x and our negative, or f of negative x, are equivalent, then we know that f is even which is symmetrical about the y-axis. In the second example here, it already gave me what g of x is, so now I'm just looking at what is g of negative x. When I take the negative x cubed, then the negative cubed is still going to be negative, so I still have negative x cubed. And then if I have positive 1 over negative x, I'm just going to move that negative to the coefficient and call that negative 1 over x. At this point, what I'm going to do is I'm going to factor the negative out of those first two terms, and I'm going to call that negative of x cubed plus 1 over x. And as we can see here, I have the x cubed plus 1 over x, I have the x cubed plus 1 over x, except for one of them is positive, and one of them is negative, which means that I can state that g of negative x is the same as the negative version of g of x. And from what we've already discussed, that means that g is odd, which is rotational symmetry about the origin. And that's it.